Morning everyone. Today's a bit of a different sort of lecture. Everyone please. So a bit of a, different sort of content. Some of it's going to be fairly non-school syllabus type stuff. Anyway, the intro, drop-in's still happening. Today straight after the lecture, every other day of the week, 12 to 1. Redemption's due. Quiz A2 due in a maths drop-in by Friday. So still stick some A1s in. A few days late, but just stick some A1s in. Everyone, please. No other actual announcements at the moment. So what is it, week 5? I'll start talking about mid-semester soon. That's going to happen in week 6, followed by a 2-week break, but we'll get the test done before the break. If anyone's got any holidays coming up that's going to have you miss week 8, if you can get in touch soon. I'm arranging mostly for those to do them early. If anyone's got holidays that were booked before New Step. But anyway, just get in touch if you've got a holiday that's going to stop you from doing your mid-sem in week 8. But today, okay. What's different about today is we're going to talk about relating some function. When we say function, it just means it's a formula, okay, an equation, some relationship between x and y. That's some function. And we've got some picture of the function. Now, we're not saying that you have to do all sorts of advanced things, even though it's going to look that way. Because the concept we're doing is, well, it's covered in advanced. But we want you to be able to look at a function and tell which of these given pictures, say, might represent it. And it's all just about joining dots. Okay, if you can plot a single dot, you can work out which function it may be or might not be. So at the moment, you may or may not have logic. Why does y equals x squared look like that picture? Well, we want to try and get that. So firstly, the way we're showing it is just by doing some points. You're not going to be doing this, okay? No test is going to, on this lecture, is going to have you plotting all these dots and joining them. Why are we doing it then? Just so you can see, why does that look like that? Why does a y equals x squared look like a parabola? That's it. And if you're ever in doubt, you can always plot some dots yourself. But we're just going to make a bit of sense of it. And this, Neil's looking at power functions just because I'm saying, I don't care if you know what they're called or not. Okay, you're not getting tested on the name of these things. Just here's a function. Which picture does it go with? Now the first one says y equals x. Can anyone already think about what a y equals x graph would look like? Just a line, it's a straight line. It's gradient of 1, it's got a y-intercept of 0. That's like y equals 1x plus 0. So I already know you're going to be that line that's 45 degrees. But of course, I can always, if in doubt, I can always just do it. If y is equal to x, that means the y value, when x is minus 4, the y is the same. So me subbing in that function there, well, that's a pretty easy one to do. All the y values are equal to x values. And there was a question in last week's quiz and in the Kahoot saying something like, if it's passed to 0, 0 and 4, 4, what's the name of the line? And so 0, 0 and 4, 4, we're talking about the same line. There's 4, 4, 4 and 4, 3 and 3 was here, 2 and 2. Now the axis is not to scale, so it's, because again, the y-axis is much more compressed. But anyway, there's good old y equals x. What if we stuck a squared on it? Not just y equals x, but y equals x squared. Gut instinct to a lot of us will be, well, okay, I reckon that's a parabola, just from seeing it before. The main thing I want to do here is why. Why does it look like this smiley face thing just because I write squared there? Well, a few points tells us why. I'll just start with 0. If x is 0, 0 squared, 0 times itself is still 0. 1 times itself is still a 1. 2 times itself, okay, we're starting to get an increase. 3 by itself is a 9. 4 by itself is 16. So it really is starting to take off. Okay, so that's just the right-hand side. 0 goes with 0. There's the point 0, 0. 1 with 1. 2 with 4, 3 with 9, 4 with 16. And you can see it's starting to get half a smile. Why does the left-hand side also give us the same smile? Because negatives when times by itself become positives. So it's got this pure symmetry going on there. Minus 4 times itself, minus 4 times minus 4 is 16. You see the symmetry that happened there? So why does an x squared curve look like that? Because it's perfectly symmetrical, because negatives and positives give the same answer, and because it gets steeper and steeper, because 4 squared jumps to 16, 5 squared jumps to 25, it keeps jumping up higher. So that's the first one. Even just if that one makes sense, we'll be able to make sense of all of these ones to say that why does an x squared look like that? Because when we plot a few dots, it does. Y equals x cubed. On one side, it's sort of going to look like an x squared. Like the first, it's just going to be a bit steeper. Like if I did what I did in the last one. 0 cubed means 0 times 0 times 0. Still 0. And 1 cubed means 1 by 1 by 1. It's still 1. 2 by 2 by 2. Well, that got to be 2 to the 4 times 2 is 8. 3 by 3 is 9, but by 3 is 27. So yeah, much steeper. It's taken off hugely. 4 by 4 by 4 gets you out to 64. So sure, I might still go through that point there and through 0, 1. But by 2, it's up to 8. By 3, it's up to 27. By 4, it's off my chart. So it's still just like an even happier smile. But what's different is going to happen on that side. Yeah, it's going down. Negatives when cubed, and you line up 3 negatives, they don't all pair up and make pluses. So it's like it's sort of going to be like a parabola with half of it swung down. So if I put minus 1 times minus 1 times minus 1 stays minus, that stays minus. They're all the same numbers, just the opposite sign. So you can see there's still a type of symmetry there. It's called rotational symmetry. But again, we're talking about not plotting them accurately. If at the end of this you know y equals x looks like that, well, that was previous week. Y equals x squared is going to look something like that. And y equals x cubed looks something like that. That's all we're after, the basic shape of it. So again, if I plotted them, they'd come down here. So far we've looked at mainly a straight line, a parabola. And again, don't care about the technicality. It's got a special name, the parabola. And that cube curve, I'll refer to as a cubic, okay? But it's no big deal. That goes with that, that goes with that. On the next page, well, it starts with y equals minus x. Well, we just did y equals x, so hopefully we'll be able to work out already. It's just like that y equals x, but it's got a minus 1 gradient. I could put a 1 there. I could put a plus 0. So I already know it's going to look like that. Okay, imagine it's going through the origin. It's going downhill like that. Okay, so there's that one. It's going through minus 4 with 4, minus 3 with 3, and so on. Minus 4 with a minus out the front becomes plus 4. A minus 3 with a minus out the front becomes plus 3. So all this function does is turn minuses into plus and pluses into minuses. What's minus 0? It's 0. When you put a minus out the front of 0, it's meaningless. Okay. Any gut instinct of y equals minus x squared is going to look like? That was y equals x squared. Stick a minus in front of all those y values. Yeah, that's all it's going to do. And where's it going to flip? On the axes. Because on the last page, minus 4 squared was a 16. That's still the truth. But now there's a minus out the front. So I do the squared first, which says minus 4 squared is 16 with a minus. It's just upside down. All the same numbers coming out, but they've all got a negative out the front, well, except for 0. And again, we're not going to have to plot them all. If it made sense that all it did was turn a parabola upside down, you got it. My points were 0, 0, and a minus 1 went through minus 1, minus 2 went through minus 4, minus 3 through minus 9, minus 4 through minus 16, and do that all symmetrically. Yep, there she goes. Just turn it upside down. So, again, what do I really care about? I know that y equals x cubed was that really steep parabola here. The only difference was, on the negative side, it went negative. So what's going to happen to that if I stick a minus out the front? Instead of looking like that thing, what's it going to do? Yeah, it's just going to swap. Instead of being up there, it'll be down there. Instead of being down there, it'll be up there. It's going to be the exact mirror image of what we drew before. Because a 4 cubed is still 64. and that says put a minus out the front of me. Okay. A minus 64, a minus 27, a minus 8, a minus 1 naught. Minus 1 cubed is minus 1, but put a minus out front of me, 2 minuses. So everything just turned up. So my naught still went through naught, my 1, minus 1 was up at 1, my minus 2 was up at 8, my minus 3 was up at 27, my minus 4 was off the chart, and went down here as well. So great. If you know what an x cubed looks like, you know what a minus x cubed looks like. And again, I might not be leaving enough time to plot all the dots. If so, just even to sketch these shapes at the side, because that's what matters. Okay, so more stuff. Quadratics. Now, we don't need to go into why they're called quadratics. I'll just state that they've got a squared in them. Okay? And a square is a four-sided object. That's how it's got its name. You think a quadratic function should have the number 4 in there somewhere, because quad means 4. But the 4 is just the fact that there's a square. Okay? So y equals x squared is already graphed. We've seen that. But just look at that and imagine if you did exactly the same as this, but now there's a 3 in front, times everything by 3. What does it do to my parabola? Or now does it push it up? No. 3 times naught is still naught. It's still anchored. It's still going through here, but it gets steeper. That's all it's going to do. A times 3 just makes all the y values really steep. It's like that cubic. It's just steeper. The main thing to note is, because it'd be easy to think, well, do I just push it? No, 3 times naught squared is still naught, so it's still going to be anchored here, okay? But everything else just got steeper. Minus 4 squared was 16. It got times by 3 to give a 48. 3 9s is 27, 3 4s is 12, 3 1s is 3, and it's still got its perfect symmetry going on. Okay, all it did was get steeper. So minus 4 is up at 48, I'm off the chart. Minus 3 was at 27. Minus 2 is at 12. Minus 1's at 3. And then naught, and then the pure symmetry. Okay, great. Y equals 3x squared looks steeper. As I was saying, if you get a question that shows you y equals x squared, you've just got to know y equals 3x squared looks like that. Okay? Not accurately, just steeper. And gut instinct should tell us what y equals half x squared is going to look like. It just flattens. All those y values that were there just got half that height. So it just makes a flatter bowl type shape. So if I look back at the originals, when it was just x squared, y became 16. If it's half x squared, it's just half of all those values. Half of the 16, half of the 9, half of the 4, half of the 1, but half of the naught, still naught. So it's still just passing through the origin here, but it does these. So there it is. So the moral of that one is purely y equals x squared is black, red is steeper, half is flatter. Okay. Which of the following? This is the sort of question I get asked, and it's, I understand if that question, especially 10 minutes ago, would look horrific. But let's rule some out. Which of the following might be the graph for y equals 3x cubed? They're all x cubed type stuff. They've all got that snake shape of an x cubed. Anyone see anything that either could be right or could be wrong? Red, you're saying for right? Agreed. Red, and the main thing I'd look at is this still passes through. Even me just chucking in. If I had no idea what a function looked like, I would plug in x equals naught. When x equals naught, well, 3 times naught cubed is still naught. So it passes through naught, naught. Absolutely. That gets rid of. The green one doesn't pass through naught, naught. Okay, definitely not green or purple. Both red and blue pass through naught, naught. But if they're telling me y equals x cubed is here, 3x cubed would be steeper. So exactly, the red one's the only one sitting there in that direction that's steeper than the x cubed. Okay, so red, perfect. Which of the following might be the function for the red graph? Given that y equals minus x squared is the black dotted one, and we're looking at that, we can see, well, it's still negative, but it's, would you call that steeper or flatter? It's steeper. Just because it's upside down, it's steeper. So it's not a half type situation, it's a 2 type situation. Just imagine the upright parabola, it got steeper then flipped. Yeah, that'll do. So which one's that implying? C, absolutely. Yep, it's upside down, the minus, and it's steeper, not flatter. Great. Okay, Dropbox, shut up. Y equals 1 on x. Y equals 1 on x squared, y equals 1 on x cubed. Okay, I admit we're getting a bit nastier here, but I still stand by you could have no idea, do some dots, and you'd nut it out. And also note, clearly this is where resource sheets can help. Normally this time of the year, people's resource sheets just become little squiggles and what's called what. Totally acceptable. I was talking to Ben this morning, he said, yeah, I mean, that's part of the skill you're learning. Put whatever you want on the resource sheet. So you'll probably have lots of little sketches, that's fine. But remember, if we ask you one that's just really odd, just do some dots. This y equals 1 on x. Well, let's do some dots. And this one's going to cause more issues than most. Does anyone know what it's going to look like? 2 lines separate from each other, because we've got a real problem in the middle. Because the answer to 1 on 0, that's a bit of a concept problem. What's 1 on 0? Can't do it, it's undefined. You can call it infinity. Because 1 divided by 0 is saying how many zeros in 1. It's saying, if I've got $1, how many zeros can I give you? Infinite. How many zeros can I take away from 1? So what we say there is, no answer, not applicable. It's undefined. Okay, so I'm not going to draw a dot on there for x equals 0. There is none. Okay? But the others I should get answers for. 1 on a minus 2 is literally minus a half. 1 divided by minus 1 keeps its negative, it's just negative 1. 1 divided by minus a half, I know it's minus, and it's asking me how many halves are in 1. We've got the calculator anyway, but how many halves are in 1? It's 2. It looks odd. A whole number divided by a fraction is a bigger whole number, but yeah. How many half pizzas are in 1 pizza? 2. And it's got a negative. 1 on a positive half is 2, 1 on 1 is 1, and 1 on 2 is literally a half. So if I just plot them, minus 2 went to minus a half, it's about here. Minus 1 went to minus 1, and minus a half went to minus 2. A half went to 2, 1 went to 1, and 2 went to a half. That wouldn't answer everything for me, but I know it's not like I'm not going to draw it going through and then coming back, because there's no answer. It doesn't cut it, the y-axis at all. It doesn't touch the y-axis. X doesn't equal 0. What we actually have is a situation where it's going off to minus infinity on that side, and it's going off to plus infinity on that side. So yeah, as Jordan was saying, yeah, it's 2 separate lines. It's called a hyperbola. Don't care. Not testing on that, but it's the oddest looking thing. And also let's think back to week X, when 2 maybe, we looked at inverse graphs and we said, look, if A is inversely proportional to B, or let's say if X is inversely proportional to Y, it became, instead of Y equals KX, it became Y equals K on X. It told us, stick the other variable on the bottom. That's all this is, okay? There's overlap here, it's the same thing. That's just an inverse curve. When one thing got bigger, the other thing got smaller. That was the curve for if I had a $300 present, and it depends on whether 2 people are joining me to purchase it, share the purchase, or 10, or if it's rent. The more people we had, the less the rent, the less people, the more the rent. It's all inverse. So that's what that one was, and there it is. Now, let's not even... I just want to go back to sketches for a second, because it's a concept that really matters to us here. What would happen to that curve if suddenly that denominator, and I'm only talking rough as guts, got squared? I know that squared makes things steeper, okay, fine. But something different's going to happen here. If you get negatives and square them, what happens? They go positive. That's it. So even just... We'll look at it properly in a sec, but this number, which is small, if it gets squared, well, it's going to go up here. Yeah, pressed it. This one, you can see that the blue and the red, that's what happened when we squared everything. And overall, I don't care that it's steeper. As long as we know that y equals 1 on x looks like these things. Positive x's make positive y's, negative x's make negative y's. But if I'm drawing it down here, if I'm squaring everything, it's ending up like that, okay? There's going to be nothing down the bottom if negatives are all squared. I'll do the actual numbers. If, before we said it was, oh, no, it was 1 on x, sorry. That was minus a half, minus 1, minus 2, no answer, 2, 1 and a half. Then if it was that on that squared, now it's a 1 on 4. Now it's a 1 on 1. Now it's a 1 on a quarter. And it starts to look like that. Okay? A half square is a quarter, so we've got 4, 1. So that's me proving the point I was trying to make, that it's got symmetry. As long as it makes sense to us. Squaring puts everything up in the positive region, not negative. So what about a cube? Well, you can see the green one's already shown. Does it make sense that if we said y equals 1 on x looks like that, if I squared everything, everything's up there. What if I cube things? Does cube get rid of negatives? No. If you cube a negative, it stays negative. 3 minuses, it still stays a minus. So basically the sketches that we care about, might seem odd, look pretty much the same for y equals 1 on x and y equals 1 on x cubed. Okay? The sketches, which is our rough drawings, are the same thing. And look at the actual lines. The first one was red, the last one is green. Yeah, same thing. Same enough. Okay? But the blue one was positives. Okay. Now this one is just saying, what about with inverses? I've got no squares in there, but what happens to an inverse if you chuck a minus out the front of it? Well, it's the same as before. The first inverse is already drawn there. What would happen if we put a minus out the front of that? It'll come, yeah, you can look at it that way. Or that everything that was plus here will now be minus. Everything that's minus here will now be plus. Okay. So everything that I plotted here, it's all the same answers, but instead of minus half, it's half. Instead of minus 1, it's 1. Everything just swaps sign. So purely like that. The minus made it red. It's the same as the concept between the cubics. Our cubic looked like that. Our negative cubic looked like that. They just swap. Everything that was here is now there. And the y equals 2 on x. Well, I'll just go back here for a sec. If y equals 1 on x looks like that, all I want to prove to you here is y equals 2 on x makes stuff all difference. If the number was 2, if it was 10, if it was 100, it's still going to look pretty similar. Okay, it might get steeper, flatter, it might change its height, but it's not going to change where the answer is. 2 on x, well 2 on minus 2 is minus 1, 2 on minus 1 is minus 2, 2 on minus a half is minus 4. I still can't put 2 divided by something. Divided by 0, it's always going to be no, just no. 2 and a half is 4, 2 on 1 is 2, and 2 on 2 is 1. So it's told me that minus 2 goes with minus 1, minus 1 goes with minus 2, minus a half goes with minus 4, 4, half goes with 4, 1 goes with 2, 2 goes with 1. Shut up, Ben. And I'll just put the third. Look at blue and black. In terms of a sketch, they're the same. Doesn't matter what number goes on top. Sure, it might change its steepness, but it still, as a sketch, looks exactly the same. Whatever, if you just got an x on the bottom, y equals 2 on x. If someone wanted me to sketch y equals 100 on x, it might be really, really steep, but I'm still just going to draw like that. That's its sketch. Okay. So which of the following might be for y equals 10 on x? What's it doing to it? Anyone confident enough? Given that y equals 1 on x, looks like that. Y equals 10 on x still looks the same. So it's still a okay? Putting a 10 on the top didn't actually change anything sketch-wise, okay? Pluses still gave pluses, minuses still give minuses. Yep. What about that one? Y equals minus 1 on x squared. Let's go in for the jugular a bit, but just split it back. I'd look at that in 3 parts. I'll think, what does y equals 1 on x look like? Then I'll think, what about y equals 1 on x squared? And then I'll think, what about y equals 1 on x squared with a minus at the front? The 1 on x I know looks like that. What does the squared do to it? Step 2. Went up positive. What would the minus do to that picture? Get both positives, take them down. Okay, so 1 on x definitely looks like that. The x squared made them all positive, but you now stick a minus out the front of this answer. It says a minus out the front of all them. It's D. I'm looking at a worst case scenario, but was that doable? Yeah, just with the concepts of squared make things pluses, but a minus out the front chucks it back under. All right, what other tricks we got? Root functions. What's drawn on there is not a root function. That's just, normally if I'm going to put a graph on a thing, y equals x squared, we just get used to it. It's old mate. After we're finished with these, we still carry on a little bit with y equals x squared. But y equals root x is quite a different looking function. Let's just try some things. I'll start naught again. What is the square root of naught? Naught times naught is naught. What times by itself to give 1? 1 does, so root 1 is 1. What times by itself to give 2? It's not a pretty answer, this one. What times by itself to give 2? In other words, what is root 2? Well, we've got a calculator now. Root 2 would come up at 1.4, blah, blah, blah. It's not a pretty number. I'm just going to write approximately 1.4. Root 3 is also not a pretty number. It'll come up as 1.73, blah, 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 about 1.7. But root 4 should be pretty. What times by itself to give 4? 2. So you see that between whole number answers, yeah, we're going to have some decimals, and I'm not going to plot them accurately. What about root minus 1? What times by itself to give minus 1? What times by itself to give minus anything? That was an imaginary number. There is no answer. There's no real number. No number can multiply by itself and give you a negative. It's either plus times plus or minus times minus. There's no answers there, okay? Which, as the one popped up, there it is. That's a unique one. There are no answers to the left of the y-axis, and the points we had was 0, 0, 1 went through 1, 4 went through 2. Yeah, that's y equals root x. A fairly easy one to pick compared to the others because there's nothing on the left-hand side. And what tells me that? As soon as I see a square root sign, I know I can't square it a negative, so that helps me write that one. What if every number there got times by 2? Overall, what would happen? Instead of being that half curve, what would happen if we times everything by 2? Would it shift it up by 2? Parts of it would look it. Would it still go through the origin? 2 times 0 is 0. It's going to stretch up. Okay, it's like that parabola. The parabola didn't just go up by 2, the parabola stretched up. Let's do the numbers. There's still no answer here. 2 times root 0 is still 0, but 2 times root 1 is 2. All these numbers just went up. So my 0, I've still got to go through there. 1 is now up at 2, and 4 is now... Oh, what did I do there? And 4 is now up at 4. It just got steeper. There's the blue line. So y equals root x is the red line, y equals 2 root x is the blue line. Again, all you had to know was you stick a 2 out the front, times something by 2, it gets steeper. But 2 times 0 remained 0. Okay. Which of the following could be true for y equals negative out the front of root x? I'm not trying to square root a negative due to the negative out the front, but it still tells you what x values I can have here. And again, I would look at the one step back. And the one step back to me is y equals root x looks like that. So what would y equals minus root x look like? Which one, sorry? B, C. We've got a few varying. It rhymes with P. They all rhyme with P. Caitlin, nothing? All right, fine. What happened to things that were here and I stick a negative out the front of it? It goes down there. Okay, anything that was up, you stick a negative out the front of it. What was up there is now down here. What was up there is now, yep, it's just that one. C. Okay, so that's y equals root x, but you stick a minus out the front of it, and naught's still naught. Everything goes minus. End of the road, okay? And I'll admit, we're not going to focus on these a lot this week. Exponential functions is more next week. All we care about this week is what's the approximate shape of them, okay? Next week, there's some little cheats that will be able to tell us stuff and be a very applied thing. This one just says, in general, what do these things look like? And that's all this page is doing. So you don't really need to sketch everything if you don't want to, but we'll get a concept of the shape of these things. Y equals 1 to the x. It's a bit of a trick question in a way. What's 1? I'm going to start from the right. What's 1 by 1 by 1? What's 1 cubed? What at 1 squared? 1. 1 to the 1? 1. See the pattern? Yeah. 1 to any power. And the calculator confirm it. I won't go back into all the indices laws. We just don't need them. Okay? But all that is, y equals 1 to the x is purely the straight line. I may as well just have written y equals 1, because there's no power I can raise 1 to make it change. It's just 1. There's a reason for that madness. Why bother even plotting it then? There's a reason. We'll come back to it. The next one says y equals 2 to the x. Now that's going to have some different answers. Saying whatever x is, let's work out 2 to the whatever it is. Well, let's start from the right again. 2 times 2 times 2 is an 8. 2 times 2 only, 2 squared is a 4. What about 2 to the 1? Anything to the 1 stays itself. 2 to the 0, we said anything last semester, to those who were with us, anything to 0 was 1. And again, we've got a calc, not that concerned about it. We said a minus power meant 1 over. So 1 over 2 to the 1 was that. 1 over 2 squared was that. 1 over 2 cubed was that. What I find more interesting in this is the overall pattern. Start at an eighth. An eighth times 2 is a quarter. 2 quarters is a half. 2 halves is 1. 2 times 1 is 2. 2 times 2 is 4. Exponential graphs always do this. They always keep multiplying by whatever that number is. In the top one, we just kept timesing by 1. Didn't change much. In the one under, we keep getting times by 2. Yeah, everything kept doubling. So if I was going to think about what does that look like, well, at minus 3, I'm down at minus an eighth. Too small for me to accurately plot. At minus 2, I'm down at a quarter. It's still too hard. At minus 1, at least I'm up to a half. Then I'm up to 1. Then I'm up to 2, then 4, then 6, then... 2, then 4, then 8. And then I'd be up at 16, and so on, so on. That's an exponential curve. Okay? Exponential growth just looks like that. And that's why next week we'll take this one further and say, what about a population of rabbits? So 2 rabbits, then after a month I had 4, after another month I had 8, after another month I had 16. That's exponential growth. So we get a concept. What do these things look like? Them. And what happens on this side? You can see on this side, my sketch is horrendous. But it's forever getting closer and closer to 0, to the x-axis. But it's not touching it, because even 2 to the minus 100 is 1 over 2 to the 100, which is 1 over some massive number. So it never actually touches the axis, but it forever approaches it. And on the right, it just takes off forever. What's going to be the difference between y equals 2 to the x and y equals 3 to the x? 3 squared, 2 squared is 4, 3 squared is 9. 2 cubed is 8, 3 cubed is 27. Steeper. On one side, it's just going to be steeper. Because whereas we were at an eighth, a quarter, a half, 1, 2, 4, 8, if it's 3 to the x, well, 3 to the 0 is still 1. 3 squared is 9, 3 cubed is 27, Sorry, 3 squared is 27, 3 cubed is 81. It just keeps times by 3. If I move to the left, it keeps dividing by 3. So that's a third, and that's a ninth, and that's a 27th. So just look at the difference between red and blue. Red is y equals 2 to the x, blue is y equals 3 to the x. They still pass through a y-intercept of 1, because 2 to the naught and 3 to the naught are still 1. Just blue takes off steeper. And on this side, hard to tell if blue is actually under red. Okay? So, yep. What's happened? The white... But no, did I? It can be. In base... Thank you. 3 to the 1 is 3. 3 to the 2 is not 9. Yep. I got ahead of myself. 3 cubed is 27. Thank you. So it takes off real quick. What about a half to the x? If that's y equals 3 to the x, and that's y equals 2 to the x, where do you think y equals a half to the x is going to lay? Also, the first graph I drew was deliberately to say, here's y equals 1 to the x. Clearly, y equals a half to the x. Well, it's not above here. Let's just plot some numbers and see what's happening with it. It's something that keeps getting times by a half. Not keeps getting times by 2 or keeps getting times by 3. It keeps getting times by a half. It's going to be the opposite. It's going to be getting smaller. So if I've got a half to the minus 3, if I did that in the calculator, I'd get an 8. A half to the minus 2 would give me that. A half to the minus 1 will give me that. And you see what's happening? I keep getting halved. So at minus 3, I was up at 8. At minus 2, I was at 4. At minus 1, I was at 2. And then we cut there again. So what's the big difference? That's exponential decay. So if you've got yourself a number greater than 1, if you're times by something greater than 1, you must be getting bigger. If you're times by something less than 1, you must be getting smaller. So it's an exact mirror image. Y equals 2 to the x and y equals half to the x with the exact mirror image of each other, that one and that one. Just one's growth, one's decay. Which of the following might be for 1.2 to the x? So it's not 1 to the x, it's not 2 to the x, it's going to be in between them. Okay? Would you agree that's still going to be growing? If you get a number and keep timesing it by 1.2, it's going to go up. Okay, y equals 1.2 to the x, it's still going up. What about y equals minus 3 to the x? Let's take it back a step and a minus on the previous page. Y equals 3 to the x look like that. If you stick a minus in front of it, what's it going to do to it? Just picture all those plus, like that plus number comes down here. That is down here, that. Do those help? It's got to be C. Okay, if you stick a minus out the front, there it is at C. All right, same rules. Another one. What if it's 0.7 to the x? No negatives involved, nothing's chucking it under the axes. But is it going up or is it going down? You keep timesing something by 0.7, are you increasing it or decreasing it? Times by anything less than the number 1, you've got to be making it smaller. It's got to be B. You keep times by 0.7, you keep getting smaller. It's not growth. There's no minuses out the front, just that one. So this is just a bit of a summary. Where I'm saying, okay, we might have done a lot of dots there. What mattered? Y equals x. My sketch for y equals x, that's meant to be going through the origin, is just, I know, it's just positive 1 gradient through the origin. If you know that, that's good. But y equals x cubed, I know it was like a half a parabola there, but the other half was upside down. If I know that's y equals x cubed, gold. Y equals minus x, Well, that was the same as this one up here, but it had a negative gradient. So that will do my sketch of that. Minus x cubed, remember, the negative of this one just meant that swings down here, and that swings up here. Okay, what else we got? We said y equals x squared was a parabola. Yep. Again, no, that's horrendous. What about that? It's pretty good. Okay, there's a parabola. Y equals minus x squared. Just chucked it upside down. Yep. Y equals root x. That was an odd one. Anyone recall what it looked like? What was different about it? Yeah, it was only to the right. It didn't get bigger. Or it was getting bigger, but at a less rate. But it was the odd one that was like, it went through 0, 0, 1, 1, 2, 4, and it had nothing on the left. Yep, y equals root x. And again, no big change. You stick a minus out the front of it. All it does is reflect it in the x-axis. There's y equals minus root x. Okay, so minus always just reflects it, gives a mirror image in the x-axis. Y equals 1 on x. What was that beast? Yeah, it was the two things. There. It was the hyperbolas that had two bits. You think, well, God, was it those two quadrants or was it those two? Just remember, if I put a positive x into that equation, will y be positive or negative? If I put x equals 2 in, y will be a half. They're still positive. So if I put a plus into there, a positive x will still give me a positive y. But a negative x will give me a negative y. That's why quickly remembering, yeah, it's those quadrants. Positive gives positive. Here's positive x, here's positive y. Plus gives plus, minus gives minus. But if you stick a minus out the front, I'm going to reflect everything. That was up there is now down here. That was down here is now up here. Y equals 2 to the x. After next week in particular, we're going to look at them and see, just look at that and see, you're timesing by 2. You keep timesing by 2. And the other unique thing about it is I always know that when x equals 0, 2 to the 0 is a 1. Don't have to remember it anymore because the calc's there. But that's what happens with these exponentials. And the same thing's going to happen with y equals half x. The only difference between this graph and this graph is it's going downhill. It's still passing through 1 there, but it keeps halving. It went from a height of 8 to 4 to 2 to 1 to a half to a quarter and so on. So there's a summary of sketches before we hit the quadratic. But since we break up there, let's have a 10-minute break there. We'll come back to the quadratics.
You're saying that this one is 1x.
Now 1 to the power of 0 is a 1. We've got a rule that says anything to the power of 0 is a 1. So that, and that, they're all 1s. The unique thing about all of these things is they pass through with 1. I'll just put the time right. I'll just be a sec.
So half to the power of 0
Is also still 1. Just be a sec. And there. Yep. Yep. Go on.
So you're saying that with this one, 2 to the power of negative 2 is negative 1 over 4.
It's 2 to the negative 2. It's not an actual negative answer. Here we're not going to bother about the what. I'll still explain it to you.
Yeah,
2 to the negative 2 means 1 over 2 squared with no negative.
Yeah,
So just a
You
quarter.
put it as a negative.
Did I?
Negative.
Oh, idiot. Sorry.
So I was just like,
I'll explain that in the thing.
so like, it'd be like that.
Yeah, exactly. Right, I'll mention that.
And also, how do you do that?
Well, A half.
Don't just power versus both of them.
You do. But also the minus can mean 1 over, which is the same as flipping it. So minus makes it a 2 on 1, which is 2, and cube makes it 8. So you can just consider that minus power just turned upside down, and then everything to the cube.
So it'll be 8.
Yep, exactly. Beautiful.
This question here, how do you know how to sketch it before leaving it out?
You've done it. A basic sketch of the situation. What's thrown to me really close. I mean, you've already done it. We'll work out how you can see. We know the height of the cliff as well.
Yeah.
But for the moment, your basic sketch, you've already done it.
Yeah. And the initial, that,
Yeah.
how do I work
What does
that
initial mean? Initial.
like
what-
where it started?
Yeah. What does time equal to at the start? At the start of this lecture, I could have said time equals 0, and our lecture starts at t equals 0. If that t was a 0, what would happen? What would it tell you? It would tell you the height is equal to 150 plus 20 times 0 minus 10 times 0 squared.
So it's just 150.
The number that's standing by itself. You can also think of it as like it's the y-intercept. It's the initial value.
Okay.
Everything else disappears. Yeah,
Thank you.
cool.
A redemption sheet? Yeah, one.
I have.
Was this the problem with the is that right?
Yeah, because minus 4, we do minus 4, minus 9, and minus 4, and minus 1, and minus 1, because it's a round. No, but that's because you've got to put in brackets. Put your mind, put brackets around your minus 4. If you just write if you write minus 4 squared in a calculator, it says I'm going to square the 4 and then times it by minus. But what we're really asking you is if x squared and let x equals minus 4, the question is really what's minus 4 all squared. What we mean is get the entire minus 4 and times it by itself. So if you put that in your calculator, it'll be correct. But if you only put that in the calculator, it'll be wrong. Yeah. Cool.
Quick question. So with the drop-ins,
Yeah.
so can I just go in there and like ask for help for like anything? Okay, cool. Because as
Not academically listening.
yeah,
You
no.
can't
Why would
ask
I
us for
ask?
help in that.
Yeah, no. So
No, it's not working.
so basically, can I have do you have a redemption sheet on you or anything?
Yeah, someone just... Why aren't you moving? Move. Thank you. What we started about...
We started
Yeah.
at 10 to.
Yeah.
Yes, the time. Thanks. Because because the week 3 stuff, I had no idea.
Okay.
Like, I'm really struggling with I'm struggling to wrap my head around like the formulas and like the concept of it.
Yep.
As you can probably tell, because I got 1 out of 10 for my.
Okay, well, this will help, and just come to ask us, and then you go, oh, okay. And you'll say things like, oh, is that all you meant? Is that
Yeah.
all?
Yeah, because I'm like struggling to wrap my head around like the week 3 stuff.
Cool. Okay, carry on with this, and we now just focus on the quadratic for a bit. Okay, so the quadratic function, it is the y equals x squared 1, but it doesn't always look as simple as y equals x squared. Notice firstly, a quadratic function is of the form, and I know that looks a bit horrendous, but what matters there? It's just saying where a and b and c are constants, as in they're just a number, okay? But the highest power it's got in it is a squared. So this is a quadratic because it still basically contains, not going to write for me now, awesome, escape, your point, where you go back, we will write, okay. Y equals x squared bit is right there, okay? So the highest power x happens to is a 2. So yes, that instantly tells me it's a parabola. And the other numbers, well, we'll get to them, okay? So that is a quadratic. You can see it's not going through the origin anymore. Might have been y-intercept, it's been lifted a bit. We're not going to go into that too much. But yes, the highest power is an x squared. That's still a quadratic. The highest power is x squared, it just happens to have a minus, okay? It's still quadratic. That one, yep, still a quadratic. It's got a 30 at the front, doesn't matter. The highest power of x is x squared. That one you might think, well, is that a quadratic? No, it's a cubic. Okay, they're all named after the highest power you see. The highest power you see there, that's still a cubic, and it's like that other cubic. It's got that snake shape, not a parabola. And that one, well, that's clearly not a parabola. It doesn't even have a squared in it. So, parabola is a graph of a quadratic function, meaning anything with this x squared in it. And no higher power of x. We've already looked at this. The first part of the lecture. These used to be 2 separate lectures. Minus 3 squared went to 9, minus 2 at 4. So we already saw, why does a parabola have a smiley face looking thing? There it is, just subbed in. Perfect. And we already looked at before, well, what happens if I stick a minus sign out the front of it? Okay, it's the exact same thing, upside down, but still passing through 0, 0. So, here's one that isn't the standard. So this one here, it's got this minus 2x bit and this minus 3 bit. That minus 2 doesn't tell me anything in particular that I can go straight to the graph with. That minus 2, I think, does that mean it moved horizontally? No, it just, we're not even going to deal with it. If we were doing advanced maths, we would factorise that and it'll tell us certain things. We're not going there. As long as we can see that you're still a parabola and you're still upright, because there's not a minus in front of the x squared. And here, I'm just plotting it just so we can see what it does look like. Minus 2 went with a 5, minus 1 with a 0. So if that's a sketch, there is one thing that the sketch told me that we should be able to pick out, and that is just the y-intercept. Okay? What worked for the straight line still works for these. The number that stands by itself is still your y-intercept. Okay? In other words, the y-intercept happens when x equals 0. If I chuck an x equals 0 into that equation, well, what happens? That becomes y equals 0 squared minus 2 times 0 minus 3. Everything disappears except for that minus 3. And you're not going to, sometimes? Okay, imagine a circle around that minus 3. So, the number that stands by itself is always the y-intercept. All right. Some other things. Already said it. That okay, if the x squared has a positive in front of it, in other words, nothing, no negative, then it's upright. If it's got a negative, it's upside down. Notice this one, it's a bit, when a is positive, it has a minimum value. In other words, why do part, okay, why does that have a minimum value? Just because it does, best explanation ever. That has a minimum value because it bottoms out here. It doesn't have any values under here. When we talk about a function having maximum and minimum values, we're talking about the y values. Does this parabola have maximum values? No. It goes up forever. Okay? So an upright parabola has a minimum value. An upside down parabola has a maximum value. It's a little bit the opposite of what gut would tell me. I'd think maximum value, well, does that mean it's right way up? No. Minimum value, maximum value. And the variation of a, well, what changes? If y equals 2x squared, we already looked at this in the first half as well. We said, well, that made it a lot steeper. And we already looked at that. What if I stuck a half out the front? It made it flatter. Okay, so we've already been here. That might not look flat enough, but if it used to go up to 9, now it goes to 4.5. If it used to go to 8, a half in front only goes to 2. So that's exactly to scale what these parabolas are looking like. This is all just background info. And notice this as well. You can always align a parabola to have an axis of symmetry. Okay? It's never skewed off that way. If you've got yourself a parabola, and say the parabola cuts, say you've got some sketch which isn't even very good, and say it goes through, that you're told it cuts through 1 there, and it cuts through 7 there. I know for a fact that means it's 6 along here, which means it's 3 here and 3 here. I can promise you the axis of symmetry cuts through an x of 4 there, okay? Because it's always perfectly symmetrical. So we've talked about maximum values, minimum values. Are they upright? Are they upside down? They've got an axis of symmetry. And here's a formula. Like I said, we're not going to actually plot these things out, but we're interested in where the axis of symmetry is, especially if I'm like throwing a rock. This leads into projectile motion. What I might really care about is what's the maximum height it reached. Well, I want to know where's its axis of symmetry. So sometimes the axis of symmetry will be easy, and if you're given a picture, like I did on the last one, easy. But sometimes you're just given a formula, like this example here. Y equals x squared plus 4x plus 3. I don't know, and I don't want to sketch it. And we're not going to learn how to sketch it. Okay? We're just going to use this formula, where x equals minus b on 2a. And where does the b and the a come from? Just this form. The a is the number that's multiplying the x squared. So in other words, what's there? Well, that must be an a equals 1. Remember, an x squared has a 1 out the front of it, not a naught. A naught will make it disappear. If there's nothing written there, it's got to be 1. So this has an a equals 1. The b times the x, that must be b. Also make sure, are they plus or minuses? But you can see here they're both pluses. And the c isn't used for the axis of symmetry. Okay, I don't care where the y-intercept is. It doesn't change the axis of symmetry. So that's all I need. So let's just go for it. A is 1, b is 4. And I chuck it in. The formula says x equals minus b on 2a. We'll explain why x equals in a minute. But so it's a minus 4 on 2 1s. Remember, that's the times. So a minus 4 number on 2 times 1. It's minus 4 on 2, which is minus 2. So the overall answer is not just minus 2. We started with x equals. I think, what is x equals minus 2? A few weeks ago when we said, what's the name of this line? We called that maybe y equals 3. So a horizontal line was called y equals, like, if it was passing through there, we called that line y equals 3 because it cut through y equals 3 with a gradient of 0. We also said vertical lines were called, maybe that's called x equals 2. That's what it's doing. The answer to an axis of symmetry question for a parabola is x equals something because it's a vertical line. And here's the picture which we wouldn't have to draw, but which shows what I'm talking about. It said the axis of symmetry is x equals minus 2. Agreed. That looks perfect. So the axis of symmetry is not just the number, just quoted. It's like, marks in it. X equals minus 2 is the name. So let's do another one. What's the axis of symmetry of that? And I'm only going to sketch it without using some advanced maths. I don't know how to sketch it, okay? Other than just doing some dots, and it'll take me ages. All I care about is this here. I'm getting rid of that answer. What other answer do you reckon I can get rid of? Yeah, it's not y equals. Y equals are then. No upright parabola has an axis of symmetry horizontal. So it's either B or D. Absolutely. Let's check. My A value here is whatever's times in the x squared. Notice I'm not just saying it's the first number, because maybe they'll write it round the wrong way. The A is attached to the x squared. The A here is a 1. The B is attached to the x. Make sure you grab the entire thing. That 2 owns assigned to its left. Let's sub into the formula. X equals minus B on 2A. It said minus B. So if B already has a minus, and it says put a minus out the front of your B, it's got to become plus. Okay, that minus is there, but b itself had its own minus. It becomes plus. It's 2 on 2. X equals 1 is my answer. But I swear if that was a quiz, most people are going to call that x equals minus 1 because there's a minus in the formula. But if you've got a minus in the formula and you chuck a minus in, please make it plus. Another one. Okay, this one's got, well, the a is sitting there. It's not minus, it's a is just 3, and the b is this minus 12. All it is a substitution exercise. So x equals minus, and the b is a minus 12 on 2 a's. All right, minus minus 12, it's plus. 2 by 3 is 6. 12 and 6 is 2. X equals 2. Yeah. Okay. And I'm not sketching it to prove it. I don't know. I've just got to be careful in my calcs. But x was equal to 2. A third one here. Okay, it's been written back to front. A is not 2. Okay, just because it's written first. 2 is the c in this. A is whatever's in front of the x squared. In front of the x squared is a minus 1. It just says minus, but everything's got a 1. In front of the b is a 4. So as long as I'm plugging that in, I'm all good. X equals minus and a 4 on 2 minus 1s. The top didn't become positive, but the whole thing's going to, because I've got a minus 4 and a minus 2. So I've got a minus 4 and a minus 2. The two minuses make a plus, and 4 and 2 is 2. X equals 2 was its axis of symmetry. It was upside down, but upside down things still have a vertical axis of symmetry. I don't care. So, good. Axis of symmetry leads us to the next thing we care about. And there's two main things we care about on any applied problem with parabolas. Where's the axis of symmetry? And maybe, if it was upside down, what was the maximum height of that rock? In order to do that, before we go applied, we're going to talk about the vertex of a parabola, which is just its turning point. Okay, that's its vertex. And you can see, yeah, that's probably a pretty critical part of a parabola if it's talking about the firing of a bullet or a cannon or whatever. It is. So the vertex is an actual point. So if I'm going to describe that vertex, I'll describe it in the full x comma y thing. I'm not going to have something that says vertex equals 3. 3 is not a point. It's got to have an x and a y. So, to find the maximum minimum value of a quadratic function, we need to know the vertex. In the one pictured, I'm finding the minimum value of a function. Okay? But how do I find it? I always use the axis of symmetry. The beauty of the vertex is the vertex always sits on the axis of symmetry, whether you're upright or upside down. Okay? Might be some horrid thing, whatever. But I know that that vertex lies on the axis of symmetry. So if I can find the axis of symmetry, maybe I'll just make one up. If the axis of symmetry is x equals 4, I promise you the x-coordinate of the vertex is 4. Okay, it's sitting on 4. So if I can find the axis of symmetry, half my vertex question. Can we not have the chat at the back? It's probably pissing some people off there. Cool? Okay. So if I can find the axis of symmetry, I can find the first number, I can find the second number, so I'm just going to chuck it into whatever equation you've given me. If the equation of this was whatever y equals x squared minus 2x plus 3, if someone said, well, it can't be. If someone said, well, the x-coordinate is 4, I can just plug that 4 into here and find its mate, the y-coordinate. Okay, we'll do some examples in a sec. So all we're going to do to find vertex is find the axis of symmetry. Formula will do the job. Then sub that x into the equation to find the y-coordinate. It might be a minimum value, might be a maximum value. If a is negative, we've got maximum. If a is positive, we've got minimum. So we'll check them in a sec. Find the vertex of that. The graph won't be given. I've left the graph there just so you can see what it is we're doing, but the graph won't be given. It'll just say find the vertex of this. Initially, we've already done this. We'd find the axis of symmetry. We did that. We said x was minus 2. So part of my answer is always done. The x-coordinate of the vertex, part of my answer is an x-coordinate of minus 2. The picture backs that up. We can see from the picture the y-coordinate is minus 1. But to find the y coordinate without the picture, we just say, well, if x is minus 2, chuck that into the original function. You must tell me where the y is. So if I chuck x equals minus 2 into that function, it tells me y equals, get x and square it. These brackets are important. Remember, if you're subbing in, if it says square minus 2, your calculator might, oh, that just reminded me. Apparently, in a grid before, for what was it? One of the, I think maybe for y equals 2 to the x. Apparently, I wrote something like, I wrote a minus a quarter. Okay? If you notice me, I accidentally wrote a minus in there. I didn't mean it. Okay? I was pretending. Back on that page. Someone just noticed, yeah, I stuck an errant minus in there, or I said minus. I didn't mean to. Those exponential ones were all above. But apparently I put an errant minus in there, so apologies for that. If you're looking back at that thinking, why do you write minus? I just didn't. Okay? Alright, so if we sub all this in, minus 2 squared is a 4, 4 to the minus 2 is a minus 8. Okay, when x equals 2, y equals minus 1. Exactly. How do I quote the answer? The vertex is at minus 2, comma minus 1. So axis of symmetry is an x equals something. Vertex is a something, comma something. Okay? The minus 1 represents here, so the minus 1 is the x coordinate was across minus 2, and the y coordinate says it came down to minus 1. Yeah. So we called that point minus 2, comma minus 1. The other way that question could have been worded was, find the minimum value of this function. Well, the minimum value of the function is just the y coordinate. How low does this function go? It goes as low as minus 1 and no lower. So max or min is asking you, the highest y or the lowest high. The highest y or the lowest y. We'll get back to that in a sec. Got some examples coming. This sheet shows it. Here's the questions we could get asked. It's got an axis of symmetry, x equals minus 2. Check. The vertex is minus 2, comma minus 1. Yep. And its max or min value, in this case, minimum value, because it's there, is minus 1. In the worksheet this week, we've got to arrange them to show exactly that, some practice on that to show this is how you answer all these questions. Let's do one. Find the vertex and hence maximum value of that function. Now, if it said max or min value, I'd know it's maximum anyway, because it's y equals minus 2x squared. It's upside down. Yeah, they've got maximums. But it told me in the question anyway. As soon as it says vertex, I know I need the axis of symmetry. I don't know where this curve is. Let's just make it look like that. I want to know x equals what? Okay. The formula on my resource sheet says x equals minus b on 2a. That's my axis of symmetry. My a in this question is what's times in the x squared, which is minus 2. And my b is a positive 4, whatever times the x. So I've got a minus and then the number 4 on 2 times a minus 2, which is a minus 4 over 2 minus 2 is minus 4. Just 1. Minus on minus is a plus. 4 and 4 is 1. Yep. X equals 1. So instantly I know that the vertex is at 1 comma something. How do I find the something? I've got to chuck my x equals 1 back into the original equation. That equation at the top tells me where every dot sits. All I'm going to ask it is, well, if x equals 1, what's my y? Well, y will be, when x equals 1, it'll be minus 2 times a 1 squared plus 4 times 1 minus 3. Purely subbing into that. 1 squared is 1. Minus 2 times 1, is minus 2. Plus 4 minus 3. Minus 2 plus 4 is plus 2. Minus 3 is a minus 1. So as soon as I found my x coordinate, my axis of symmetry, I chucked it back in and found my y. There's my point. I'm not going to check it on my graph because that will take ages. The only other thing, what's the maximum value? Hence, what's the maximum value? The maximum value is that. That probably sounds like a pretty poor maximum value. But this thing must look something like something like that. It's cutting the y-axis there. Its maximum value is -1. It just doesn't go higher. It's an upside down parabola with a max of -1. Something like that. Okay? Okay. Now we've got more of this coming. It's going to be more applied. Instead of just x, y, it might be height, time, a rock, a stone, whatever. Millsback, just to see as we lead into application, a pretty important question is why do we care? What's so good about a quadratic function / parabola? Well, know what happens when rays reflect on a parabolic surface. See that one there? We've got this focus in the middle. If I've got rays coming down to meet a parabolic surface, it's built so that each ray that reflects will actually meet at the one point. And it goes both ways. Firstly, if I've got some focus there, say it's a light bulb. So if I've got a light bulb here that's shining rays out at every angle, every time it hits here, it's actually forming a parallel beam. Like that one, the headlight, where the tip of it is coated so that it doesn't go out at different angles from here. Everything is forced to go these directions. That's how we can get a horizontal beam so we're not blinding the person in front of us when we put our lights on. Admittedly, I don't know if I put in the technical, admittedly there is a little thing to make it a bit less so you can adjust it so it actually beams it down a bit so it's not quite in their rearview mirror. But yeah, there's parabolas in our headlights. Here's another one. What about the exact opposite? If I've got parallel rays of whatever going towards a parabola, well, it'll focus everything, bounce it into the centre, which is good for that. The focus of that dish clearly is right here. This parabola is made so it focuses right here. So all that does is collects better signal. Okay? It focuses all this signal from a good area into one spot where it's picked up. So why make it that big? Yeah, just to create a better focus. Here's another one, which is a good solar energy sort of thing used in the outback. If I put a collector tube in the middle, so flowing along this way, if hot oil was passing through here, and I've got these parabolic mirrors, and so they're just trying to get as much sun as possible instead of just a solar cell where it's just heat me up. No, it reflects it all back, and all of these are reflecting back into this one pipe, and that pipe carries oil and gets heated up, which then goes and converts to electricity. So those things are fairly impressive. You can see what I did there? So we're still not examinable. Neil's watching, okay. But I just thought it's horrendously interesting. And they're also pivoted, so they can follow the sun and get the maximum energy out of the sun. Yeah, just with mirrors and a tube of oil. Well, a good-sized tube of oil. And yeah, so there's 258,000 mirrors, and they're tracking as in following the sun. So yeah, that covers an area of 2.5 square kilometres, power thousands of homes, or just from the sun and a bit of energy to pump the oil around. So it's not too shabby. Bridge construction. We see parabolas there. Definitely, if you look at this, I'm pretty impressed with myself here too. I calculated that formula from a picture. I don't know if it's what they used. But if you look at that parabola, that perfect parabola is exactly what has been used on the underarch of the Sydney Harbour Bridge. And again, it distributes, like before we distributed the rays evenly, that distributes the weight evenly. Okay, so it's not one particular part of the bridge, it's getting caned. You want to distribute the weight on a bridge. Same with San Francisco. It's an upside down parabola, but it's it's an upright parabola. Sydney's upside down, but it's distributing the weight. And as we get back in time as well, they discovered it's not a perfect parabola, it's a fairly old bridge, and they used a lot of like viaducts, used circles. Circles are strong, the parabola's better, but you know, they were still going for this strength. But mostly what will we consider, our practical exams will mostly, if not nearly all, is firing something. You know, a stone, a rock, they'll nearly all be upside down parabolas because it's a nice concept that's easy to focus in on. Neil's still watching, so don't think we're not turning into a history course. A lot of this topic is fairly interesting, and we're overlapping a little bit with physics now at the moment, I know that, but I know some in the room will be doing physics and have been doing projectile motion. Out of interest, Galileo is the bloke that really spent a lot of time with this projectile motion, came up with the equations that we now use and the concepts. So he was called the father of modern science. He was the man in terms of projectile motion, at least. I put in 5 quick facts about Galileo. He correctly claimed that the Earth rotates around the sun and not the other way around, that the Catholic Church said. So he was sentenced to life imprisonment. So he was jailed for that. He was right, but he got jailed. But in 1992, the Vatican formally declared he did nothing wrong by going against the Catholic Church. They cleared him of doing anything wrong. A little bit late for him. Einstein was Galileo's biggest fan, so that's not a bad rap. He also sketched various inventions, including a candle and mirror combination to reflect light through a building, which is still parabolas. Okay, a little candle here and a parabola dish behind it that would give a torch. So he loved his parabolas. An automatic tomato picker, yeah, okay. A thermoscope that you see in like those geography, yeah, that's not phallic, stop it. With the coloured balls in it that float, okay, that's not good. At certain temperatures, depends where they float to. He invented that. A ballpoint pen, that was him as well. And a pocket comb that doubled as an eating utensil. I mean, awesome. He made a living, though, designing military compasses. So this is one of his sketches, and he came up with the concept that D was proportional to T squared. In terms of us, what we've been doing, what he was saying was D is equal to K number, D was equal to some number times T squared. So it's just like our questions. We could have said a cannon is fired so that its distance was proportional to the square of time. Well, he worked it out. He did all these experiments and worked out that that's exactly what happened. And so he was a good wartime person and found out that the height above ground, a quadratic function of time 2 seconds, quadratics modelled objects in the air. Okay. So that leads us to here. Now, 2 main types of questions we're going to have for you. One is, okay, we might have graphed it. So it's an applied type. Can you read a graph? And can you get the concepts of projectile motion? The other will just go, no picture, just the formula. Firstly, this graph shows the path of an object thrown in the air. So the first change we've got to handle is that the y-axis is not a y-axis. It's an h-axis here, because we're talking about height in metres. And the x-axis is actually a time axis. So this way we're doing time in seconds. Okay, we handled that last week with the straight line graphs. We'll handle it this week and say, okay, your form is something like h equals t squared. Maybe some other numbers. H equals 5t squared, minus 5t squared, whatever. H versus t. How high is that object above ground level after 1 second? So it is just reading it carefully. Anyone? Yep, 15 metres. You can see there that after 1 second, we just read the chart, and it's 15 metres high. Remember to give it its units. Okay, the units are always in the question or on the axes. Either way, the height was said in m, in metres, so 15 metres, perfect. At what time or times is the object 10 metres above ground level? Okay, yeah. So you're putting that about 2/3. So we've got, I'll put in the dotted line. So of course the hint was maybe there's more than one time. As we said, parabolas are perfectly symmetrical. Okay, you might debate that if we're talking air resistance. We're not going there. Okay, parabolas are symmetrical. So at what times is the object 10 metres above ground level? The only issue with this one would be, are you reading accurately enough? If we're going between 0 and 1, if I count us through and assume there's 10 boxes, well, 1 divided by 10 is 0.1, so that's 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So 0.6 seconds, said before, and 3.1, 0.2, 0.3, 3.4 seconds. Okay, again, there the units matter, and just read it as accurate as you can. All right, that one's pretty easy to read. All right, if it was in between, then some people might get slightly different answers, but just give it a go. So you get 0.6 and 3.4 seconds. All right. What is the greatest height reached by the object? Well, we can see it there. It's a nice accurate graph. It's clearly hit at 20 metres. And yeah, that's what happened. When did the object reach its greatest height? Again, just slow down the wording on the question because it's when, so it's not asking for the 20 metres. What's it asking for? Yeah, when did it happen? Well, clearly it hit its greatest height at 2 seconds. Okay? And if I wasn't sure, definitely, it's a 0 to 4 second thing. Symmetrical, it's always going to be halfway. So, yeah, after 2 seconds, that's when it reached its greatest height. How long does it take for the object to fall from its maximum height to ground level? Yeah, 2 seconds. Perfect symmetry, and it just means from there to there, 2 seconds. Okay, yep, no traps, honestly. 2 seconds. For how long is the object above a height of 17.5 metres? Well, we could find 7.5 metres. Clearly it's going to be exactly halfway between the 15 and the 20. So halfway between the 15 and 20 is there, and we can see that it's above that height for just the top of that thing, but we want the time. So if you can look at, if you can find those 2 times, clearly it's the bit between it. Now whether you work at this time and work at this time and do a subtraction, we would have said, hang on, every one little box was 0.1 of a second. So there's 1, 2, 3, 4, 5, 6, 7, 8. Hang on, did I get a 7? Let's just double it if I did. 1, 2, 3, 4, 5, 6, 7. Yep, and I'm going by the symmetry and say there's 14 little boxes of 0.1. So 1.4 seconds. Whichever way you worked it out. I could also have seen that that was a 2.7, that was a 1.3, and the gap was 1.4 seconds. Perfect. Okay, so if it's given to you, that's pretty nice. What about this one? A rock is thrown into the air, and this is the where we're heading, definitely with the questions. Thrown into the air from the edge of a cliff into the sea. The height of the rock above sea level in metres at time t seconds is given by that formula. I actually meant to remove that. Don't get put off, please, by this H bracket, T bracket. I forgot I took it out this year. It's just called function notation. Which what it means is H is a function of T. It's a technical thing just saying, you give me a different T and I'll find you a different H. I'll make sure that doesn't happen on quizzes and stuff. Don't worry about it. It just means H equals that. It just meant T makes me change. Okay? Doesn't matter. H equals 150 plus 20T minus 10T squared. So it's a formula that will tell me the height of this rock if you sub in a T. A basic sketch of the situation could sound like, well, what? Very basic. A rock is thrown in the air from the edge of a cliff into the sea. Yeah, that's a sketch. We can add to it. All I'm saying is I don't know, to be honest, I don't know whether he threw it up. I mean, if I drew the same sketch and said, I don't know, did he throw it horizontally? Did he throw it heaps up? They're all the same sketch. The formula contains that information. I can't tell you at the moment. All I'm saying is, yeah, it's some parabolic thing, and I'll hopefully add more information to my sketch. Now, what was the height of the rock initially? Where's that info coming from? C, exactly. The y-intercept, just think, as soon as you say the word initially, it means at the start. And call this an experiment. This was an experiment. And it started at t equals 0. So all it's saying is, what's the height when t equals 0? Well, if that t was a 0, and that t was a 0, I'd be writing 150 plus 20 times 0 minus 10 times 0. What's that going to give me? 0 squared. All the 0 stuff's just disappearing. My answer is 150. In other words, that c value, that y-intercept, they're all the same thing. Just told you where you started from. We started from 150 metres. Okay? So this cliff was 150 metres high. Don't worry about if you're thinking, hang on, how tall was the bloke? You know, if he stood on a 150 metre high cliff and he was 1.5 metres. Don't worry about those little things, okay? We're not going there with how tall the person was and all that. We're just saying the rock started 150 metres above the sea level. So there's my sketch. The height of the rock initially was 150 metres above sea level. 150 metres would have done. We know what we're talking about. Okay, what else have we got? When will the rock reach its maximum height? So if I go back to my sketch, And assume, if you're asking that assume it's something like that. It's asking me for this point here. Not the height, but when. It's asking me for a time. You want to see what I'm going to do to try and work that time out. It does happen on the axis of symmetry. And since the x's are t's, instead of x equals, it's t equals. Good. It's going to calculate the time. The axis of symmetry in this graph, normally we say x equals minus b on 2a. If they were x values, they're not x values. So this is going to tell me the time at which it's at its axis of symmetry. That's exactly answering the question. Okay? It's at its maximum height when time is whatever this answer is. Well, let's find out. And if this comes out and says time equals 0, that means it was at its maximum height when I threw it. And I didn't throw it up. But if the time is anything positive, it means it's at a maximum height. I must have thrown it up a bit. Let's just sub in. My a and b values. My a is what multiplies the t squared, and my b is what multiplies the t. So it's minus b, which is a minus 20, over 2 lots of a. Don't forget it's got a minus. A is minus 10, not just 10. So there's my formula. It's a minus 20 over 2 times minus 10, which is a minus 20 over minus 20, which is just the number 1. And the units here, we were told, is seconds. So my sketch is pretty accurate. All right? I'm not talking about, we don't care, like you say, well, how far out did he throw it? We're only talking about, when we talk height, it just means distance off the ground. I don't care how horizontal it went out in the ocean. It's just irrelevant. We're just talking about the height of the rock above sea level. And it reached its maximum height after 1 second. That's it. And we're not changing this. We're not going to suddenly talk about horizontal. No. When did the rock reach the maximum height? 1 second. What was the maximum height it reached above sea level? Well, let's chuck it back in. Basically, we've asked for the vertex. Remember, the vertex was find the axis of symmetry, and then you could find the height. That's what we've done. The axis of symmetry in this case was a time, and we knew it happened at t equals 1 second. If I want to know the height of the rock after 1 second, well, that's just it. The height equals 150 plus 20 times t, which is a 1, minus 10 times t squared, which is a 1 squared. So it's a 150 plus 20 minus 10 ones, which is 10. And the units matter again. So the axis of symmetry was time in this case. Fine. The maximum height occurred at that time. Chuck it back into the original formula. What's the maximum height it reached above cliff level? Any thoughts? Back to a sketch. Just 10. Okay? If we're saying the initial height of the rock was 150 and the maximum height the rock got to is 160, it's just saying, well, how much higher did it get from where it was launched? Just the difference between the two, 10 metres. Okay? So there's no new formula. It's just adding to your sketch, your basic sketch you had. That was the maximum height it reached above sea level, or cliff level. All right, what else you got for us? A quick check. What was the initial height of the rock thrown according to that equation where h is in metres? Where's the initial height in that? Anyone? This C sound's coming out. Yep. The initial height is always when t equals 0. T equals 0 always gets rid of anything with a t in it, and all you're ever left with is whatever number is by itself. Left, right, centre, don't care. And it's set in metres, it's 1 metre. The initial height of this rock was 1 metre. So it's actually a very nice question. It's just the number left when all the t's wreck everything else with zeros. The number that's by itself. This one, how a rock is dropped from the top of a 100-metre tall building with a height above the ground given by that formula. T's in seconds, so okay. How high is the rock from the ground after 1 second? It's a nice sub in. All you've got is a formula that tells you the height after certain amounts of times. The question just says, well, what is the height after 1 second? Fine, sub in. h equals 100 minus 10 squared. So after 1 second, it's 100 minus 10 by 1 squared. Order of operations says do the 1 squared first, which is 1. 100 minus 10 times 1, 100 minus 10. Okay, so the rock is still 90 metres above the ground. In other words, it's only fallen 10 metres during the first second. Was that the next question, maybe? How high is the rock? When we subbed in 1 second, it tells us it's still 90 metres off the ground. How far did the rock fall in the first second? 10 metres. It started at 100 metres high, initial. It was at 90. All right. It fell 10 metres. How high is the rock from the ground after 2 seconds? All right, I'll chuck a 2 in there. 100 minus 10 by 2 squared, 100 minus 10 fours, 100 minus 40. So it was dropped from here. In the first second, it went from 100 metres to 90 metres. During the second, it speeds up. You know, the rock will speed up if you chuck it off a building. So at 60 metres, how far did it travel in that second? It went from 90 to 60. So in the first second, it travelled 10 metres. In the second, it travelled 30 metres. Okay, so this one leads to that again. Here's another one. We've got a graph and a formula. But notice this graph's going to be hard to read at certain points. So the fact that we've got the formula might help us. H is the rock's height above the ground, C is the times that it was thrown. Okay, H is in metres, times in seconds, all nice and consistent. What was the time of flight of this rock? In other words, how much time did it spend in the air? 5 seconds all up. You can see it launched at naught, it was hit the ground by 5. So yeah, 5 seconds. No trap, just 5 seconds total flight. Use the graph to estimate the maximum height reached and when this occurred. Well, when this occurred isn't an estimate. Either I can look, it's exactly on the 2.5, or I know that it's going to be on the 2.5 because it went between 0 and 5 seconds. Halfway is 2.5. There it is. But what I'm estimating is it's not a good graph. So let's just say I need to count my boxes up a bit. I've only got 4 boxes between 30 and 40. So in a gap of 10, I've only got 4 boxes. 10 on 4 is 2.5. So each box is worth 2.5. So if that's 30, that's 32.5. That's 35. Well, if that's 32.5 and that's 30, it looks about halfway in between them. Okay? About 31.25, 31.5, something like that. Either of them would be fine. If I just rounded and said, about 31.5 seconds, I'll be marked right. I'm in the right ballpark. Because it was estimate. But use the formula to calculate the exact height. Okay, that's where I'm going to be able to be accurate, because I got given the formula. So just because you're given a sketch, if it asked for exact, go back to the formula, because it's exact. Well, h equals 25 by, it's a 2.5 minus 5 by 2.5 squared. So 25 times 2.5 is 62.5. Minus 5 by 2.5 is 5 by 5 on 4, 25, 6 1/4. So we got 62.5 minus 31.25. Something like that. Equals 31.25. So our estimate was pretty good. But anyway, that's doing it exactly. Okay, we've answered all the questions good so far. When is a stone travelling its fastest? Overall concept. When is this stone the quickest it's ever going? At the moment it's released from the hand, if it's been thrown. When else? The moment it hits the ground. Perfect symmetry. And that'll be true. Okay, ignoring air resistance. That if there's perfect symmetry in this thing, it'll be the fastest at the moment it leaves your hand. And also at the same time, say you caught it, it's at the exact same speed it left your hand. It's got to be, ignoring air resistance. Calculate the average speed of the stone during the first second. All right, during the first second. So here's the first second. It says average speed. Now, we don't have many practical formulas that come in, but we have been saying from the graphs, speed is distance over time. Okay? That's about the only thing, and notice you got the, if it ever helps, use the DST triangle. Distance, speed, time, or David Stewart Thompson, it works both ways. If you get asked about when is a stone travelling at this speed again, that's asking for a time. If you cover over that time with a finger, you'll only see D on S. That's saying time equals D on S. That's what we said last week. Okay, well, actually we didn't have one of those graphs last week. Last week we had speed. If you cover over the speed, you'll see speed equals distance on time. That's what we had last week. A distance, vertical axis, and a time. We said the slope of that thing, its units were kilometres per hour, was a speed. Yeah, because speed is distance on time. And also, just to complete this little triangle, if you covered the D, it'll say D equals S times T. It'll say the distance equals speed times time. So it's just a useful little thing for any practical little problems when you're in doubt. We want to calculate a speed. It says speed equals distance on time. In the first second, what distance has it gone? Okay, first, 20. In the first second, it's gone 20 metres. In what time? A second. What's 20 divided by 1? 20. And the units still tell me the story, metres over seconds. There we go, that's all it was. That probably sounded a lot worse. What was the average speed of the stone? It was 20 metres per second. Is that it, is it? Sweet. All right. Done. Welcome.
That A always looks like that, B always looks like that, and C always looks like that.
Always. But just remember that, so the A is just a number. Then take the x squared with it. So if it's A, that's just 5x squared, the A is just the 5.
Right, okay.
But it's always like that.
But I should always look for that form when I'm looking for that.
Always.
Okay,
Yep.
thank you.
Cool. Yeah. Damn chance.
Yeah.
See ya. Yep. The actual, yeah. I'm like in that exercise there. Well, first, I was pretending that it just went straight up.
Yeah.
So the only velocity was vertical. But if it had a horizontal component, you wouldn't need to do it with Pythagoras. You'd only do that if, just say, I gave it some sideways component.
Yeah.
And if it had gone up 20 metres, but across 1 metre, your actual velocity would be what Pythagoras says.
Yeah.
But in case of this, you don't need to do a triangle with time. No. 20 metres per second was exact there for the average. Yeah.
Okay, so
But yeah, if it had horizontal, you'd exactly do that. Yeah. You do in physics? Yeah, so you'll split them all into horizontals and verticals.
Yeah.
Whenever we're just...
okay, all good.
Yeah.
Just checking about my quiz. Last.
Yeah.
I didn't get my marks back, and I just wanted to know if.
Oh. I marked it and okay. Polo, Yep, I'll make sure it's up. I know I've got it, yeah.
All right,
It's all
thank you.
good. Okay.